So let's recap. We've learned quite a bit so far. We've talked about parameters and statistics. We've talked about discrete and continuous data, different types of sampling and research designs. We visualized data, looked at measures of center, talked a little bit about degrees of freedom, and we've used SPSS to make box plots and touched on z-scores, amongst other things. So where are we going? We're going to look in this chapter at the standard normal distribution. We're going to look at real applications of them. We'll look at sampling distributions of sample statistics, talk about the central limit theorem, briefly assess normality. I have this section crossed out because you'll see once we get to the binomial distribution, we can approximate it with the normal distribution, so I've left that out. And then we're moving into students T at the end of this chapter. So I think I'll do this in two sections. I'm going to go through sections 1, 2, and 3, and then in the next video I'll do 4 and 5. Okay. So in this section we're going to talk about the characteristics, the probability of some z-values, and find z-scores for the standard normal distribution. So when a continuous random variable has a distribution with a symmetric graph and it's bell-shaped, it's considered normal. In a standard normal distribution, the mean is mu, so that's the parameter, is 0, and the standard deviation sigma is equal to 1. And the area under the curve also is equal to 1. Important information about uniform distributions is also that area under the curve is equal to 1, and there is a correspondence between area and probability. Okay, so if you're looking at the normal distribution, here we are with a mean of 0, right in the middle, there's mu, plus or minus 1 standard deviation, plus or minus 2, and plus or minus 3 with a little bit of extra probability in the tails. If you look in the green, 68.2% of observations will fall within plus or minus 1 standard deviation from the mean. If you go out 2 standard deviations, you've captured about 95.4% of observations. If you go out 3 standard deviations, plus or minus, you've gotten almost all of the probability under that, or the area under that curve, which is also directly related to probability. So you've got about 99.7%. This is important to remember because we're going to be looking at these areas under the curve. Alright, so from page 222 in your book, here's an example. It says a bone mineral density test is helpful in identifying the presence or likelihood of osteoporosis. The result of a bone density test is often measured in a z-score. So z-scores, like I said, have a mean of 0 and a standard deviation of 1. So these results meet the requirement of a standard normal distribution. So a randomly selected adult undergoes a test. What is the probability that this person has a bone density score less than 1.27? So that is a z-score that is less than 1.27. So we always are going to want to start these by drawing a normal curve. So we just draw a normal curve, it doesn't have to be perfect. And we place it approximately here at 1.27. We're looking at area to the left because it's less than 1.27, and we want to know how much probability is it in that section of the normal curve, because that will correspond to how much probability that the person has a bone density score less than 1.27. So what do? We have to go into the back of the textbook, and the way it works is if you come over here, you see where it says 1.2. Okay, that's the z-score. I come down to 1.2 and then I slide over to 0.07, so that's 1.27. And this area, this number corresponds to 89.8% or 0.898. Okay, so what does that mean? It means that the probability that someone has a bone density score less than 1.27 is equal to 0.898, or 89.8% of the people will have a bone density score less than that. Okay, so if that's the case, then what's the value to the right of that? What is the probability that someone will have a bone density score that's greater than 1.27? Well, if I know that the whole area under this curve is equal to 1, and I just subtract 1 minus the bone density, or the probability rather, on this side of the curve, I'll get the probability on the right side of the curve. So that's 1 minus 0.898, and I get 0.102. Alright, so we can keep going. If you look in the back of the text, there are a bunch of different z-scores, excuse me, z-tables out there, and they can be presented in all kinds of different ways. The way this textbook presents it is it just gives you the probability to the left. Okay, so you're looking always to the left. But look at this. I want to know what's the probability between -1 and -2.5. There's this little piece that I don't care about, and then all this piece that I don't care about. I just want what's between here and here. So how do I do that? And this corresponds to figure 6.7 on page 224. It's the third one to the right. Alright, so what do? I'm going to go and I'm going to look up the area to the left of 2.5, and I get this bit. Okay, to the left of 2.5, that's 0.0062. And then I can look to the area to the left of -1, and I get 0.1587. So to find the area here is I'm going to take this little piece away from all of this distance. So that's, to find the region in between, we subtract the area to the left of -2.5, which is 0.0062, from the area to the left of -1. So I do this calculation and I get 0.1528. Okay? We can do that till the cows come home. But what we're going to do eventually is we're going to move into having the computer do it for us. Tables that show the area under the curve are fine, but nobody carries z-tables with them around in life. So we're going to use software to calculate these probabilities. Rule of thumb for significant values. Remember back a couple of PowerPoints ago, we saw something similar to this. We had the area, the orange area in the middle, and look, it's between 2 standard deviations. Those are not significant values. But when we get to beyond 2 standard deviations, we have significantly high or significantly low values. We can see that z-scores that are above and below negative or plus or minus 2 standard deviations are considered significant. And why do we care? So these are z-scores that above which or below which 5% of the probability lies. It can be in one tail or in both tails. So let's look at this. We've got a normal curve, right? And we've got 95% of the observations in this region, non-critical region. 95% are here, then that means 5% are here. The z-score to find that critical value is -1.645, beyond which anything that's found over to the left here would be considered significant. The probability at -1.645 is 0.05. So if I found a z-score of -2, I'm in the critical region and I am significant. If I find a z-score of -3.5, I'm way over here and I'm also in the critical region. If I find a z-score of 0.98, I'm over here, I'm in the non-critical region. If I find a z-score of +3, I'm in the critical region here, but if I'm only looking at this direction, then it doesn't count. Okay? We can look at probability. We can put all our probability that we care about to the left side, or we can put all the probability that we care about to the right side. When we do that, it's plus 1.645, and the probability is 0.05. Or we can have the probability in either tail. The critical region can be 0.025 over here to the left and 0.025 over here to the right. That means anything we find in here, any z-score that lands in this non-critical region is not considered significant. But if it's found over to the right or over to the left, it's considered significant. That's all you need to know right now about this. We're going to talk way more about this in the next chapter, in chapter 8, the next chapter that we cover. But right now, just take a good look at this and kind of let it sit with you for a second. The thing that you need to really want to take away is that we're looking at 5% or 0.05 of the probability, and that's important because when it's at or below, or actually below 0.05%, we're going to consider it a significant value. Okay, so now here's the z-score formula. We can now transform individual scores, these x scores, into standard scores, z's, by using this following equation. So what do we have here? We have the score minus the population mean, which is a parameter, divided by the standard deviation of the population. Why would we want to do this? We want to see if the score we found is significant, meaning would we have found it by chance or for some other reason? We're going to talk more about that in the following chapter as well. Alright, so let's take a look at an example. We have the proportion of males with a pulse rate greater than 100 beats per minute. We're looking at example 1 on page 232. So the pulse rate of males are normally distributed with a mean of 69.6 BPM and a standard deviation of 11.3 BPM. Find the proportion of males with a pulse rate that's greater than 100 beats per minute who are at risk for stroke, heart disease, or cardiac death. We're going to draw our normal curve, right? We're going to look at our z-score formula, and the things that we have are over here. We're looking for the z-score, so let's plug in chug. We know that we're looking for a score of 100 minus the population mean, which is 69.6, divided by the standard deviation, which was given at 11.3. We do this calculation and we find a z-score of 2.69. We just round. Okay, that goes about right here. So what we're looking for in our textbook is the probability. It only gives us the probability to the left. So we're going to go and find 2.69, and what we get is 9.9964. So the probability that a man has a BPM greater than that is what's over here. So we have to subtract it from 1. 1 minus 0.9964 is equal to 0.0036. Very small, not found by chance alone. If you'll recall, it's smaller than 0.05, and it's in this tail, so we would say that that is a significant finding, a significance. Okay, so how do we know which way to look? It says how many men have a BPM greater than 100. We're just going to follow the arrow. We're going to go to this direction. We want to know how many men fall in this range, but because of our textbook, it only shows us this, so we have to do 1 minus. Okay, another way we could do it is just use software. I got this from the internet. You can use any z-score calculator on the internet, but you just have to know which way to look. Our score is 100, our mu is 69.6, our sigma is 11.3. I plug it in, and then I'm looking, see this little red portion here? We know that we're looking to the right, and there we go, 0.0036. Okay, let's do another one. Pulse rates. Example 3 on page 235. Given that pulse rates of adult males are normally distributed with a mean of 69.6 and a standard deviation of 11.3, find the pulse rate that separates the highest 100%, the highest 1% from the lowest 99%. So we're looking for probability of 99. So here we know the probability, so we look in the table to find the corresponding z-score for 0.99, so that instead of looking, let me scroll back, instead of looking for the z-scores, we're going to look in the table, right? I don't have it here, but we're going to look for the one that says 0.99, and then find the corresponding z-score, okay, which we found is 2.33. So the part we're missing is X. We're looking for X. So we know this piece, we know this piece, we know this piece. We do a little bit of algebra and we solve for X by isolating X. X is equal to mu plus sigma times Z. Plug it in and we find that the score for which 99% of the people, the lowest 99% fall is at 95.9 beats per minute. Anybody beyond that is 1%.